Okay, in this video, I'm going to go through AQA AS-Chemistry paper. This is paper 2 from June 2016. And I'll just do half the paper and the second half in the next video. Okay, so about equilibrium. Ethene reacts with steam in the presence of an acid catalyst to form ethanol. Write an expression for Kc. So it's fairly straightforward. Kc, concentration of ethanol. Over the concentration of ethene to the power of 1 times by the concentration of water of steam to the power of 1. And the units of that, well, you're going to have a mole per decimeter cubed on top. You're going to have mole per decimeter cubed on the bottom. So they cancel out. So you end up with 1 over mole per decimeter cubed. Bring everything up to the top line. So you change the sign on the indices. So that's mole to the minus 1 dm cubed. They are the units. Okay. Right. An equilibrium mixture was found to contain so many moles of ethene, steam, and ethanol. And the volume of the container was 2 dm cubed. Calculate a value of Kc. So what we've got to do is we've got to put the numbers into this expression here. Don't forget that concentration is equal to the moles over the volume, and the volume they tell us is 2 dm cubed. Okay, so I'll write down here Kc is equal to we've got 4.4 moles of ethanol over 2. That's the concentration. 4.4 divided by the concentration, 2 dm cubed. And the concentration of ethene is, well, it's going to be 0.7 over 2. And the concentration of water is 1.2 over 2. Right, now we can cancel some of those 2's out. I'll get rid of that one there with that one there. That makes the slightly fewer numbers to put into a calculator. Put those numbers into the calculator. We get 10.47. Now, appropriate number of significant figures. Well, all of those, everything here is given to 3. So we should give our answer to 3. So 10.5 is the answer, mole dm per mole dm cubed. The units. Okay. Right. This is about an enthalpy change, okay? So, right, a student carried out an experiment to determine the enthalpy of combustion of methanol here, okay? So delta HC for methanol. That's what we're trying to find out. Okay, so they put methanol in the spirit burner over the copper can with so much water in it, 100 grams of water. And then they weighed so they knew how much methanol they were burning. They weighed the burner before and then afterwards. Okay. And what we've got to do is calculate a value for delta H. Use the student's data to calculate an experimental value for the enthalpy of combustion of methanol. So the 2 equations we're going to need here are Q, which is the moles of heat released in the experiment. And that's given by Q is equal to M, which is the mass of the water in the can here, not the mass of methanol burned, times specific heat capacity of water, C, times by the temperature change. Then we need to convert that value of Q into value for delta H combustion, which is going to be equal to Q, the heat released, divided by the number of moles of methanol burnt. Okay, so that's what we're going to do. Right, so let us work out Q first of all. Okay, so Q, red, Q is 100 multiplied by 4.18 specific heat capacity of water multiplied by the temperature rise, which is 38.0. Okay, that works out to be 15,884. Now we need to put delta rate Q into this expression here. We need to work out the number of moles of methanol first. So here's the mass of methanol burnt. Let's just work that out. We've got to subtract the final mass from the initial mass. That gives us 1.65 grams. So moles of methanol is equal to the mass of methanol divided by the MR. That's equal to 1.65. The MR of methanol is 32. And that gives us 0.0515. That's the number of moles of methanol. So that's ready to go into this blue equation over here. Do that. Delta H, the value for Q, is 1580.84 divided by number of moles, which is 0.0515. And that gives us 308.427 joules. Right, we probably want to express that in kilojoules, and we want to put it in the right number of significant figures. So it's going to be 3 significant figures. Everything, all the data is given to 3. So that is going to be equal to, now it's really important, we've got to remember to put a minus in here because it's exothermic, because the temperature went up. And if you don't put that minus in, you'll lose a mark. So it's minus 308 kilojoules per mole. That is the value for delta HC for methanol for 4 marks. Okay. Let's carry on. Right, suggest one reason other than incomplete combustion or heat transfer, which is just about covers all the errors, but you've got to give a different one. Why the student's value for enthalpy of combustion is different from the data book. Well, the heat loss to the atmosphere is going to be the main thing, and maybe a little bit of incomplete combustion. They're the 2 main errors. So any other errors, I would say maybe some of the ethanol evaporated rather than burned when you put the flame out. Some of the methanol evaporated. That's about the only thing I can really think of. The main 2 errors, they've said you can't have them. Okay. Right, here's about experimental and experiments and uncertainty. The uncertainty in each of the temperature readings was 0.25. This gives an overall uncertainty of 0.5. Calculate the percentage uncertainty. Well, delta T, it told us in the earlier on, was 38 degrees C. So that's going to be a pretty small error. So error is going to be the uncertainty, 0.5, over the measurement, 38, multiplied by 100. And that gives 1.32%, which is a very small error, okay? Compared to all the heat losses and stuff. They'll probably ask us about that now. The student said that using a thermometer with an overall uncertainty of this was adequate. Explain why the thermometer. Well, it's as I said earlier, is because the heat loss errors are going to be an awful lot bigger than that. Much bigger. They're probably going to be like 30%, 40%, even 50%. So this makes no difference really. Okay, the enthalpy of combustion of ethanol is minus 1371, and the density of ethanol, they give us a calculate the heat energy released in kilojoules when we burn 0.5 dm cubed of ethanol. Well, the equations we need to use here are mass is equal to density times volume, and then we're going to have to use this equation, aren't we? We're going to have to use the quantity of heat is equal to delta H multiplied by the number of moles burned. Okay, so let's work out the mass of the mass of ethanol first of all. So that's going to be the density is 0.789, and the volume is 500 dm cubed, but this is in cm cubed, so that's 500 centimeters cubed. And that gives us 394.5 grams. Now we need to work out, we need the number of moles of ethanol here. So we need to work out our mass of ethanol, turn it into moles. So moles of ethanol is equal to mass over the MR. The mass is 394.5 and the MR is 46. So that gives us a number of moles of 8.576. 8.576 moles. Okay, so now we're going to have to put this value into here, and we're going to have to put our delta H value in to work out Q. So let's do that. So Q, delta H is 1371. 1371 multiplied by the number of moles, which is 8.576. And that is equal to exactly 11757 kilojoules. We need to give that to the correct number of significant figures, which should be, well, they give us the ethanol to 4 sig figs, but everything else is to 3, so we give it to 3. So that's going to be 118 kilojoules. That's going to be the heat transferred. Okay, so some organic chemistry now. Right, so we've got give the name for isooctane. So we've got isooctane here. So find the longest carbon chain. 1, 2, 3, 4, 5. Okay, so it's going to be pentane. And we've got 3 methyl groups. We've got 1, 2, and 3. So it's 2, 2, 3 trimethyl pentane. Now, if I had numbered that chain the other way around, 1, 2, 3, 4, 5, my name would have ended up being 4, 4, 3 trimethyl pentane, which would be the wrong answer because you've always got to give the smallest number that you can manage there. Number the chain to give the smallest numbers in the name. Okay. Octane and isooctane can be separated in the laboratory, namely technique. Well, whenever you're separating 2 liquids, it is fractional distillation. Outline how this technique separates isooctane from octane. Okay, so the main thing is they've got different boiling points. The more volatile one boils at a lower temperature, and the vapor is condensed. Now for 3 marks, I don't think you need to talk about the role of the fractionating column there. That is sufficient. So 1 mark for fractional distillation, 1 mark for different boiling points, and that's it really. Isooctane is added to petrol to increase its octane rating. Some high-performance engines require fuel with a higher octane rating. Write an equation for the complete combustion of isooctane. Okay, so we've got C8H18. I'm going to burn it with oxygen. Complete combustion, you are only going to get carbon dioxide, not carbon monoxide or carbon. And we're going to get water. Okay, so how many, we're going to have obviously 8 carbon dioxides. We've got 18 waters, so that's 9 oxygens. So that means on the right hand side of the equation, we've got 16 oxygens there, plus 9 there makes 25. So that's going to be 12.5 O2. So we've got 12.5 O2 there. Okay, explain in general terms how a catalyst works for 2 marks. 2 marks are going to always, this is a pretty standard question, provide an alternative route with a lower activation energy. 1 mark for each of those points. Okay, carbon monoxide is produced when incomplete combustion takes place. Nitrogen monoxide is also produced. Write an equation to show these pollutions react together in the catalytic converter. So what happens is you need to look, all of these nitrogen oxides, they oxidize the CO2, the carbon monoxide, which is poisonous, the CO2, which isn't poisonous, so we get CO2, and the nitrogen oxides, which can give rise to nitric acid afterwards, they get reduced to nitrogen. Right, so let's balance that. All we have to do is make that a half N2. Okay, there will all be gases, all those state symbols. Platinum and palladium are used inside catalytic converters, very thin. Why do they use a very thin layer? It's because they're very expensive metals. And it's very expensive for 2 marks. Let's say something else, I think. And the catalysis occurs on the surface. So it doesn't matter if it's thin, it's the surface area that's important. Okay, oleic acid, straight chain fatty acid, and then all they're asking is, the structure of it, all they're asking for is a chemical test. Well, the test for any, to show it's unsaturated, that means we want to test for a carbon-carbon double bond. If it's something is unsaturated, it's got carbon-carbon double bonds in it. And so the test for that is bromine water. And the positive result for that is it decolorizes it. From the reddy brown to no color at all. Okay, not makes it go clear, got to be say decolorized. Okay, so here we've got 3 isomers. Okay, explain why determining the precise relative molecular mass of propanal and prop-2-ene-1-ol by mass spectrometry could not be used to distinguish these. Right, so if you check the MR of all of those compounds, normally they're all 58. Okay. But if you did that in a high resolution mass spec, you would be able to distinguish butane from the other 2 because it's got a different molecular formula, C5H10, whereas the other 2 are both C3 even, C3H6O. All right. Propanal and propene-2, they've both got that molecular formula, so they would have precisely exactly the same molecular weight. This one would be, incidentally, would be a bit different, of course. So this takes into account the high resolution. Oxygen isn't exactly 16, it's 15.99 or something like that, and hydrogen is 1.03, it's not exactly 1. Okay, so they've got the same molecular weight, so you couldn't do that. Infrared spectrum of one of these compounds is shown in figure 4. Use a spectrum to identify the compound. Right, now it tells you should only absorb absorptions of wave numbers greater than 1500. Well, that makes telling us that is all the fingerprint region, so we can't use that. It's very generous of them to tell you that. You should realize that anyway. Right, what we've got there. Right, this is very characteristic of an alcohol, this bit here. Okay. It just looks the right shape, and it's in the right, it's an OH of an alcohol, and it's in the right part of the spectrum. So that means it's going to be the prop-2-ene-1-ol. Okay, and that is confirmed by the fact that you've got this narrow little peak here, which is very characteristic of a CC bond. Right, now how can you tell it's not the ketone? Well, if you had a ketone, ketones, they do have an absorbance in a very similar place to the CC bond, but it's a kind of a different shape. It's always a bit deeper than that one. Okay, and a slightly different value as well. So, but then also the fact that we've got the OH makes that pretty easy to tell that's what it is. Right, predict the boiling points of these compounds from the highest to the lowest and justify this into a 6-mark question. Okay, so I've reprinted the formulae. Right, so it's not hard to find 6 marks to say on this, but what we're going to say here is, right, this one can do, well, I'll explain it. That can do H bonding, which is the strongest. That can only do dipole-dipole. And this one can only do van der Waals. Okay, H bonding is H bonding is the strongest, so the highest boiling point. Then it's going to be the propanol, because the dipole-dipole interactions are usually stronger than the van der Waals. And finally, butane is going to have the lowest boiling point, because it's only van der Waals. Right, why can this one do H bonding? Okay, the reason why that can H bond, you need to say, is because you've got a hydrogen here, which is attached to an electronegative element, ON or F. It's actually O in this case. So that's going to be sufficiently delta positive to form, to be attracted to the lone pair on another alcohol group on another molecule to form H bonding. They're the strongest intermolecular forces, so that's going to be the strongest. Now, propanol can't form H bonds because it doesn't have a hydrogen attached directly to an oxygen, right? But it will have a delta positive, a partial positive charge on that carbon, because the oxygen is very electronegative. Okay, so that does have a permanent dipole, so you'll get interactions between the negative end of one molecule and the positive end of the other. So that's the next one. Now, butane can only form van der Waals forces because it doesn't have a permanent dipole, because the carbon and, you might want to say, carbon and hydrogen have got very similar electronegativity, and so there's no permanent dipole, so you can only have rise of these van der Waals forces caused by instantaneous dipoles, which then cause induced dipoles. I don't think you have to say all of that for 6 marks. Basically identifying which kind of intermolecular force for each molecule, and then a very brief description of what that kind of intermolecular force is. Okay. Chloropentafluoroethane is a CFC that has been used as a refrigerant. Draw its displayed formula. So it's ethane, so it's got to have 2 carbons long. It's got 1 chlorine on it, so it can go on either carbon, doesn't matter who does it, and 5 fluorines, so it's going to have 5 Fs. There's only going to be 1 isomer of that. Okay, display formula, you've got to show every bond, of course, yeah. Right. 1,1,2-trifluoroethane is one of the molecules that has been used as a refrigerant in place of CFCs. Explain why this doesn't lead to depletion of the ozone layer. Right, because it doesn't contain any carbon-chlorine bonds. It only contains carbon-fluorine bonds. And it's the carbon-fluorine bonds which are broken by UV to give rise to a chlorine-free radical, which then causes depletion of the ozone layer. That's far too much to say for 1 mark, but it's not difficult, I would say, all of that, just be on the safe side. Right, one of the steps in the synthesis of trifluoroethane is the reaction of difluoro with fluorine in free radical substitution. Write 2 equations to represent the propagation steps in this conversion. Okay, so now the first propagation is always when you get your alkane, or haloalkane in this case. So we've got difluoro there. Okay, and you're going to react that with a fluorine-free radical. The fluorine-free radical is going to remove one of the H's. Let's say it removes that H with its electron. So that's going to make HF. And what that will leave behind is a not a charged molecule, but you've lost a hydrogen with it. So you've got an unpaired electron there. Okay, that's a free radical. In a propagation step, you always end up with, start off with 1 free radical, end up with a free radical. And the second propagation step, right, that is going to then react with the fluorine F2 molecule. That's going to make CF2CH2F, and if you pull a fluorine off this with its electron, then you will end up with a fluorine free radical. So that's the second propagation step. Right. Right, a refrigerator contains 1.14 kilograms of trifluoroethane. Calculate the number of molecules in the refrigerator. Okay, and they give us the Avogadro constant, so we need to work out the number of moles. So what we need to use, moles is equal to mass over mR. The mass is going to be in grams, so that's going to be 1410 grams. The mR of trifluoroethane, well, it's going to be 2 times 12 for the carbons, plus 3 times 1 for the hydrogens, plus 3 times 19 for the fluorines, and that gives us 84. Okay, so the number of moles is going to be 1410 over 84, which gives us 16.785. Right, so therefore the number of molecules is going to be 16.785 multiplied by the Avogadro constant, that's the number of molecules in a mole, times 10 to the 23, which gives us 1.01 times 10 to the 25. Right, appropriate number significant figures, I've given it to 3. It should be 3 because this is only given to 3 sig figs. The Avogadro constant is given to 4, but you give it to the least accurate bit of data. Right. Concerns about use as a refrigerant, as is a greenhouse gas that absorbs some of the Earth's infrared. Suggest one reason why bonds in molecules such as CO2 and trifluoroethane, where you need to say here that they are covalent, they're polar covalent bonds. Polar bonds absorb infrared. That's why oxygen and nitrogen in the atmosphere don't absorb infrared, because of course they're not polar bonds. They've both got the same electronegativity. So I think you've got to make sure that you say it's the polar bond, not a polar molecule, but a polar bond that's absorbing the radiation. Okay. So propane 1,2-diol has that structure, and it's used in e-cigarettes and so on. A sample of propane 1,2-diol was refluxed with a large excess of potassium dichromate, okay, and sulfuric acid. Right. Now it's going, but just before we answer question 6.1, we remind ourselves that when you oxidize a primary alcohol, you go to an aldehyde, and then if there's a large excess of oxidizing agent, it will go to a carboxylic acid. And the secondary alcohol, well, you'll oxidize that to a ketone. Skeletal formula of propane 1,2-diol. Well, let's just draw it non-skeletally first of all. So we're going to have OH, OH. So let's draw that. That is that. Now, when we put on our OHs, put one there and one there. Okay. Right, write an equation for the oxidation of propane 1,2-diol under reflux. Okay, so this is going to oxidize everything as completely as possible and show the displayed formula of the product. Right, so I'm going to write down this. It's a good idea to write this down rather than do it in your head because you make mistakes. Right, so you can see there we have got 2 alcohol groups. This one is a secondary, that's going to go to a ketone, and this one is a primary alcohol, and that's going to go to a carboxylic acid. So let's draw that. So we're going to get a displayed formula of the organic product. Okay, so the end, the yellow carbon, that's going to be a carboxylic acid. The green carbon in the middle, that's going to be a ketone, and you'll have 3 bonds there. Okay, so that helps us balance in this equation. So we've got to use O to show the oxidizing agent. So just the first step is to count up the hydrogens on the left. We've got 8 hydrogens on the left. We've only got 4 on the right, so that means we've got to have 2 H2O there. Right, let's count the number of oxygens on the left. Well, we have got 2 oxygens on the left, and on the right we've got 1, 2, 3, 4, 5 oxygens. Okay, So that means we're going to need 3 oxygen atoms there. Okay, that is the equation. Right, draw a label diagram to show how you set up the apparatus for refluxing. Okay, so reflux, of course, you have your flask there. It can be pear-shaped or round bottomed. You want to show there's a little join there, and then we have the condenser in the upright position, and here's the water jacket around the condenser, and there's your stuff in there, and you should have the water going in the bottom one and out of the top one, so that the water fills up the complete jacket and it's better at cooling. Okay, and importantly, no stopper at the top. People put stoppers in the top there and thermometers and stuff. That's wrong. You have it open. Okay, and if you've got like little gaps here and stuff, they might not give you the mark. You've got to make sure it's all sealed and it would work. And also, I think they like you to show that it's 2 bits of apparatus, so that's why I've done that ground glass joint there. That's what that's supposed to be. Yeah. Right, now it says, okay, anti-bumping granules, how do these present bumping? This is, they always ask this question, and if you look in any mark scheme, the reason how they stop it is pretty complicated, but the simpler reason is they allow small bubbles to form during boiling rather than big ones. That's what you need to say. Now the last question, I'm going to copy this little bit here for the last question. Right, it says, oops. Draw the structure of a different organic product formed when the acidified potassium dichromate is not in excess. Okay, so just to remind ourselves here, right, there are actually a few different answers you can have here. You only have to give one of them, but I'll probably give all of them. Right, what could happen is let's say we don't touch the secondary alcohol, so we could end up with just a carboxylic acid there, and that stays as an OH there, so you could end up with that. Or you could have, you don't touch the secondary alcohol and you only oxidize this to an aldehyde, not to a carboxylic acid. That's another possibility. Or alternatively, we could oxidize the secondary alcohol. Let's say that gets oxidized, but the primary one doesn't get touched at all. Or we could say we oxidize the secondary alcohol and we only oxidize the primary alcohol instead of the carboxylic acid to the aldehyde. So you've got 4 different structures there, and you can have any of them. They're all partial oxidation products. And now I think that is as far as I'm going to go with this paper, and I'm going to cover question 7 onwards in the next video.